Okay, welcome. We're going to look at some problems regarding real gases from Chapter 7. So the problems we'll be looking at are problems 4, 10, 17, 24, and 26. To begin, we'll look at problem 4. 1 mole of argon, initially at 310 Kelvin, undergoes an adiabatic expansion against the external pressure of 0 from a volume of 8.5 liters to a volume of 82 liters. Calculate the final temperature assuming ideal gas and van der Waals equations of state. Assume that the C sub V sub m is 3R over 2. Starting with the facts of this problem, they want us to calculate the final temperature of an adiabatic expansion such that what is the final temperature in T external of T final of an adiabatic expansion? Well, so the first thing to note is that for adiabatic expansion, Q equals 0, which if internal energy, I know this is kind of backwards, if internal energy is equal to Q plus W, then this is just equal to W. But work is equal to negative P external delta V. And with external pressure of 0, no work can be done. So this means that no matter what, for this process, the internal energy must equal 0. Internal energy change must equal 0 for this entire process. With that in mind, we can look at how does du change as a function of T and V. The partial differentiation of internal energy would give us the du dt at a constant volume, dt, and du dv at a constant t, dv. Exchanging these proofs for our known solutions is 0 equals our C sub V sub m times n dt plus our T dp dt minus P dV. Okay. So those two things, when they sum up, must equal 0. Must equal 0. So we can do a proven integration, proven differentiation of the ideal gas problem and a proven differentiation of the van der Waals gas problem and see what we get. So remember, our ideal gas is P equals nRT over V. So the differentiation, so the dP dt of this is going to be equals nR over V. Multiplying that by T. So you'd have nRT over V minus P, which is just going to be 0. So for an ideal gas, you're going to have C sub V sub m dt plus 0 dV, meaning for an ideal gas, the right term must equal 0. In that case, for the left term, must also equal 0 if the whole thing equals 0. So that means the final temperature uh, for an ideal gas would be 310 as well. So that's the T final for an ideal. For a real gas, it's not quite as nice. For real gas, it's not quite as nice. So looking at the real gas equation, Van der Waals equation is P equals nRT over V minus NB minus AN squared over V squared. So with that in mind, the dB dt of this becomes nR over V minus NB. So the whole attractive repulsive term drops out. So when I do the nR, when I multiply by T, I get nRT over V minus NB minus our pressure. But however, our pressurized term includes the AN squared. So our equation is now simplified to C sub V sub M and dt plus A N squared over V squared dV. And all that must equal 0. So integrating both sides, we come up with N C sub V sub M TF minus 310 plus, see, integral of that would be negative AN squared 1 over VF minus 1 over VI, I do believe. Yes. Okay. And so we can now plug in our values. VF is given up there as 882. VI is 8.5. So we have 3 over 2 times 8.314. Actually, it'd be better if I left this instead of that as bar liters. So we're 0.08314 TF minus 310. A is the positive 1.355 liters squared per bar, bar per mole squared times 1 mole squared times 1 over 82 liters minus 1 over it was like 8.5 liters. And this will get us units of bar liters per Kelvin, which is going to be what we need. The right term, 1 over 82 minus 1 over 8.5 times our negative 1.355 gives us this right term to be positive 0.1429, and that would be bar liters per Kelvin, more bar liters, and times by 2 over 3 divided by R would give us units in Kelvin. So we'd get on one side TF minus 310 is minus 310 plus 1.145 is equal to 0. So 310 plus 1.145 means that our TF has to be 308.85. So our TF is 308.85. Not a huge change, but you got to remember all of that energy is coming from just the attractive force of the adiabatic. And so it's not a big force. I mean, considering the fact we usually typically ignore that force. When it comes to ideal gas. But this is in a van der Waals, so it's a little bit different. Problem 10. A 1.75 mole sample of argon undergoes an isothermal reversible expansion from an initial volume of 2.0 liters to a final volume of 85.0 liters at 310 Kelvin. Calculate the work done in this process using ideal gas and van der Waals equations of state. What percentage of work done by the van der Waals gas arises from this attractive potential? Problem 10. So in this case, we have a reversible isothermal expansion. So we can simply say the work is equal to negative P delta V. PdV. Unfortunately, pressure is apt to change in a reversible isothermal expansion. So with that in mind, we have to exchange negative PdV with the term for pressure, which would be nRT over V in the case of an ideal gas. So with ideal gas, we just have to integrate that thing, and that would give us negative nRT ln VF over VI. So ideal is actually rather easy. So 1.75 moles, 8.314 given joules, 310 Kelvin, and then natural log of 85.0 over 2.00. We plug that in. We go ahead. Oh, got a negative sign. We turn this into kilojoules. The total amount of work ends up being negative 16.9 kilojoules. Okay. 16.9 in the case of an ideal gas. Now, in the case of a non-ideal gas, this term instead goes to negative nRT over V minus NB minus A N squared over V squared dV. And so the integral becomes a little bit trickier. And so now, when we integrate that, this is going to go to negative nRT ln V minus NB V2 minus NB over V1 minus NB plus AN squared 1 over VF minus 1 over VI. So let's start plugging in some of our values. We have negative 1.75 times R, 8.314, times T, which is 310. Then ln, we have our 85 minus 1.75 times my really small 0.0320 all over 2.0 is 1.75 times 0.0320. Then plus A, which is 1.355 times n squared, so 1.75 squared over 1 over 85 minus 1 over 2.0. However, this will also need to be turned into joules. So that would have to be times by 100 to get it into from bar liters into joules. So let's calculate each side. First, our natural log. ln of 85 minus 1.75 times our 0.0320 and 2.0 minus or 1.75 times 0.0320. So that natural log term works out its way out to 3.777. Multiply by my temp, multiply by my R, multiply by our moles again. I'd get this is something like negative 17,036 joules. The other term, 1.355 times 1.75 squared times 1 over 85 minus 1 over 2. And then times 100 would be a negative 202.6. So adding those two terms together, you get something like negative 17,238 or 17,000, negative 17,238 kilojoules. So the question is, what percentage of that is coming from sorry, that becomes negative. My bad. Because when I integrate that, it becomes negative. So instead of 17,000, it's more like 16.834. So what percentage of that is coming from the attractive force? That's going to be 202 out of our 16,834. Something like 1.2%. 1.2% is the amount of work we'll be getting from that. So, problem 17. Calculate the van der Waals parameters of carbon dioxide from the values of the critical constants. Compare your results with the values for A and B given in table 7.4. So number 17 has us looking up the critical temperature values and comparing and using them to calculate the van der Waals equation parameters for a carbon dioxide. So I've already looked up the values. The critical temperature is for carbon dioxide is 304.13, and the critical pressure is 73.75. And the values from the table for the A and B are 3.658 and 0.0429. So at this point, all we have to do is plug in and evaluate. So B, to find B, it's 0.08314 times 304.13 over 8 and 73.75. You do that quick calculation, you get B to be 0.042857. Calculating, so it's a slightly more accurate version of the B they give us. least to a few more significant digits. But if I compare that, how different is that? That is less than a 1%. That is 0.1% difference in our calculated B. So not very big. Looking at our A, a little bit more difficult to calculate, but 27 times 0.08314 squared times 304.13 squared all over 64 times our 73.75. You do that, you calculate your A parameter to be 3.657298. 298. How does that compare? Divided by 3. Once again, this is even closer. The difference in our values are actually 0.010, almost 0.02% off from the values. And that's just based on the accuracy. How many significant digits do they take A out to? Essentially, it's the same. Okay, that is this problem. Problem 24. A sample containing 42.1 grams of argon is enclosed in a container of volume 0.0885 liters at 375 Kelvin. Calculate P using ideal gas, van der Waals, and Redlich-Kwong equations of state. Based on your results, does the attractive or repulsive contributions to the interaction potential dominate under these conditions? Okay, the second to last problem asks us to calculate the pressure under ideal gas conditions, van der Waals gas conditions, and Redlich-Kwong gas conditions for 42.1 grams of argon. The first step is, of course, calculating the moles and hopefully the molar volume, which will save us some bit of work because that will not change. Calculate the moles, we're going to take the grams divided by the molar mass of 39.95 grams per 1 mole. Doing that gives us molar mass of 1.053817. From there, our molar volume is going to be our volume, 0.0885, divided by our moles, 1.053817. I'm going to do that real quick and save ourselves a little bit of time. 885. So that changes our molar volume to 0.083, say 98. 8398, that's liters per mole. So to do our ideal gas, pressure is equal to RT over V sub M, meaning 0.08314 times 375 all over our 0.08398. And doing that gives us 371. The 1 point, we'll say 2. Okay. Now for van der Waals is a little bit more difficult. RT over V sub M minus B plus A over V sub M squared. So in this case, 0.08314 times 375 0.08398 minus 0.0320 minus 1.355 over 0.08398 squared. Okay, so each term, let's figure out each term. 314 times 375 divided by 0.08398 minus 0.032. So this one is 599 point, we'll say 80 minus 355 divided by 0.08398 squared minus a 192.13. So 599.8 192.13 gives us 407 point, well, let's say 407.7. 407.7 bars. Now for the Kwong, just a little bit trickier. We're always upping the difficulty. RT over V sub M minus B, that's the same. Now it's minus A square root of T V sub M times V sub M plus B. So 0.08314 over what times 375 or 0.08398 minus our B is now, B is a little bit smaller, 0.2219 minus our A is a lot bigger though, 16.86 to compensate for the square root of 375 on bottom. And then our V sub M, 0.083998, what, 8398, and 0.08398 plus 0.02219. Adding up each term again, 0.08314 times 375 divided by our V sub M minus B, 98 minus 0.02219. This term, 504.57, and then minus our 16.86 divided by the square root of 375 divided by 0.08398 divided by 0.08398 plus 0.02219. So this one's minus 97.65. So 504.57 minus 7.65. The pressure is 406.9. 406.9. So from ideal, we've gone from 371 to 407.7 and finally 406.9. So the final question is the attractive or repulsive forces prevailing under these situations? Well, you got to remember, attractive forces would decrease the pressure because they would not be pushing out as hard. So because the pressure is higher than the ideal gas pressure, means we have repulsive forces are being favored under these conditions. Repulsive forces that are subtracting out, that are adding additional pressure to what we would expect. So if the A, the secondary value, the A over Vm squared, was a larger subtractive force, so that our overall force had gone down, then we would be the pressure would have gone down below the ideal gas. We would have been favoring attractive forces. Number 26. The observed boil temperature of hydrogen, nitrogen, and methane are 110, 327, and 510 Kelvin, respectively. Compare these values with the calculated for a van der Waals gas with the appropriate parameters. The last problem involves looking at the boil temperatures of three gases and comparing them to the calculated boil temperatures. To calculate the boil temperature, you would take the A parameter divided by R times the B parameter. So I've looked up the A and B van der Waals parameters for the following gases. So just looking at that. So for hydrogen is just going to be 0.2452 divided by 0.08314 times our 0.0265. Doing that, you'd get a boil temperature of 111.3 compared to the given boil temperature of 110. Relatively close. Now let's look at nitrogen. Nitrogen gives us a 1.370 divided by 0.08314 times our 0.0387. Now, if you calculate that, you get 425.8 Kelvin, which is actually significantly larger than the boil temperature. And then for methane, following the same process, 2.303 divided by 0.08314 times our B parameter, 0431. Do that, you'd get a boil temperature of 642.7. Once again, that is significantly larger than what you'd expect with methane and what is actually given for methane at 510. So that is what all it asks us to do, to calculate that and compare the predicted versus the actual, not really do anything beyond that. You can actually look at the percent change with hydrogen. Sure, look at that one real quick. That one has a 1%, 1.2% difference. However, with nitrogen, we have a much bigger difference from predicted and actual. That one's more of a 30.2% difference. And with methane, probably a little bit smaller of a change, but still pretty significant. So 26% difference. These numbers are provided without context of why they're bigger, just that this is what they have. Okay, that's the last problem. So signing off.